Okay, good afternoon. Welcome. Thank you for being with us today for this CIS Colloquium. With this seminar series, we provide a platform that brings together professors and researchers from EPFL and researchers and thought leaders from all around the world working on different aspects of intelligent systems. Today, we are delighted to have Professor Chris Wiggins with us. Professor Wiggins is an associate professor of applied mathematics at Columbia University and the chief data scientist at the New York Times. At Columbia, he is a founding member of the executive committee of the Data Science Institute and of the Departments of Systems Biology, and is affiliated faculty in statistics. Prior to joining the faculty at Columbia, he was a current instructor at NYU and earned his PhD at Princeton University in theoretical physics. He's a fellow of the American Physical Society and is a recipient of Columbia's Evanescence Diversity Award. To give you an idea of what to expect, the talk will last for approximately 1 hour, with Professor Wiggins presenting for 45 to 50 minutes. We will then have time for Q&A. So since you're following online, feel free to put your questions in the chat and we will take them up later during the discussion. Finally, before we dive into the presentation, I would like to thank Professor Wiggins for his availability and the CIS team for organizing this event today. Now, Professor Wiggins, the screen is on yours.
Thank you very much. Share screen. Good. So first off, thank you very much for this invitation. I'm sorry I'm not with you in person in Lausanne. I hope next time. As advertised, I'm Chris Wiggins, and I split my time between Columbia and the New York Times. If there's any questions we don't have time for, please do feel free to email me later. And because this is mostly a talk affiliated with a research university, I thought it would be interesting to spend a little time thinking about what I've learned over the last 9 years at the New York Times in terms of ways that industry and academia are working for mutual benefit at present. If you would like to know more about things that we've learned trying to build up a data science team at the New York Times, there's a book that I co-authored that came out last month with Alfred Spector, sorry, 2 months ago, with Peter Norvig and Jeanette Wing of Columbia. And there will be another book forthcoming about more about the history and ethics of data coming out in in March, which I think will give more insight into things that we've learned trying to build up a data science function at the New York Times. And with that, I should say a little bit about what even I mean by data science. It means many things at different places. We've tried in some ways to have an attitude about data science that's been impacted by my own experience working in fields that have been impacted by or changed by abundant data sets. In particular, as mentioned, my PhD was in physics. I got my PhD working on biological physics. So when I started my PhD in the early 1990s, the relationship between biology and numbers was not nearly as established as it is today. And in the middle of my PhD, one pivotal moment was the sequencing of the first freely living organism, or the first sequencing of a freely living organism, which is shown here in this image. This is the genome on the right of Haemophilus influenzae. It was also, I believe, the cover image of Science magazine in the summer of 1995. That is an example of a problem in the natural sciences that had been understood already for a century. You know, even on the left, there was an image of Haemophilus influenzae as it was understood in the 19th century. And then in the late 20th century, we humans suddenly became armed with abundant data about Haemophilus influenzae in the form of its genome. However, the way that you put those data to work is really qualitatively different than the way you put the data to work in many problems in statistics or physics, in which you have an underlying model and you wish to confirm that model or estimate parameters in that model. Instead, it's a problem where you have lots and lots of data, sequence data, and no clear idea about how to relate those data to the driving fundamental questions of the field and to the community of people in that field. And I think the lesson learned in biology during the course of my PhD of becoming awash in data is in many ways applicable to what people are calling data science in different fields as the fields suddenly become awash in data. So the change was not only in the availability of a new technology and a new data set, but also just a real change in the way that practitioners of that field understood their own field and understood the relationship with data. One example piece of evidence of that is, I remember well, an essay by Shirley Tillman. So Shirley Tillman at the time was already a very well-established molecular biologist in Princeton, and then she became the president of Princeton. And she wrote this essay right around the time I finished my PhD that made the observation that the time was very exciting in biology to suddenly find itself awash in data, and that biologists would need to collaborate with people from disciplines outside of biology, which was exciting to me because by the time I finished my PhD in physics, biologists were much more interested in talking to people who put data to work in their fields day to day. Whereas when I started my PhD just about 5 years earlier, biology was, my experience was that molecular biologists, at least at Princeton, were less interested in talking to people who got in the way of more traditional methods in biology. So that was an exciting time, and it was driven by an abundant new data set and really drove intellectual questions, but also just a lot of changes in the way the different communities interacted with each other. It opened up new ways of answering old questions. As an example from my own research over this century, as my work became much more about understanding biology through data rather than through more traditional physical methods. About a decade ago, there was a virus that suddenly became prevalent in the human population. And I was working with biologists who in the early days of that outbreak were trying to understand if it was a bird flu or a swine flu, how that virus jumped from an animal population to a human population. So at the time, it may sound academic, but at the time, I think it was the government of China was trying to decide if they should kill all the birds or kill all the pigs. So we took that problem in working with a virologist, and the traditional paradigm for that was one basically established by Charles Darwin in his notebook in 1837, which is that nothing in biology makes sense except in light of evolution. And therefore, if you have a bunch of viruses, you should learn the phylogenetic tree, by the way, a very difficult statistical task. And then when you have a new virus, you should look at the phylogenetic tree and see where to put it in the tree. And then that would tell you if it's been one of the ones from the birds or from the avian or swine flus in this case. So we took that on its head and said, well, instead, let's just try to build an algorithm that can predict bird flu versus swine flu without any reference to evolution per se. And if we can show that that algorithm works on many, many genomes from viruses, then we have a statistically sound method. But if we can make it interpretable, then we can say something that's useful to domain experts. And so we did that using some machine learning methods. And again, machine learning methods that would balance between interpretive ability and predictive power, which is not always the forefront activity of machine learners. They sometimes walk into a field and they're interested in predictive power without thinking much about the role of interpretability. I should say that's not a novel insight from me. If you know anything about history of statistics, it was well articulated among other people by Leo Breiman in this lovely article from 2001, where he tried to highlight that there's really two cultures in statistics. People are interested in models that they are trying to make sense of, and people are interested in algorithms that make accurate predictions on held out data. So that's one of the tensions of trying to apply machine learning to a particular domain. So in our case, if you'd like to know more, we made a decision tree, a boosted alternating decision tree, where the primitive features were the presence or absence of particular protein elements for the virus capsid. Okay, so that is sort of one of the totems for me of data science, is that it's not just the machine learning, but it's machine learning within the context of some other field. This idea of data science, and even the phrase data science, is also, although we may think of it in 2022 as something that was just born in the last decade, a good early example of people talking about data science as a separate field is this slide, which I consider a bonus slide for academics, from Bill Cleveland. At the time, Bill Cleveland was at Bell Labs, which had a long history of heretical applied computational statisticians writing essays to academic researchers saying, there's a field here, and it's not exactly statistics, it's not exactly computation, it's not exactly databases, it's really something else. So if you'd like to know more about what people were trying to say in 2001 about the creation of a new field of data science, it was already there, and I encourage you to check that out. But most of us know data science from its blossoming or its explosion around 10 years ago. Around 10 years ago, people started using the phrase, not just data science as a field, but also data scientist as a job description. And so that was particularly led by industry. In fact, I point out before that Bill Cleveland was actually in industry, not in academia, although he was very interested in how academics do what they do, particularly training. Another industrial example is early work by Facebook and LinkedIn. So Facebook and LinkedIn are often credited as two companies that were first to start using the job title data scientist. And one of the people most credited with using that job title at Facebook is Jeff Hammerbacher. So Jeff was at Facebook, I think 2005 through 2008 or 9, and published this book in 2009 about data, including what he had learned in creating a job title data scientist and creating what we might call the first business intelligence group at Facebook. So in short, he said, we needed a new word and we needed a new job description because of the diversity of tasks being done by somebody under the name of data science. We felt like other existing job titles didn't quite cut it. And he listed a number of things that people do, which many of which align with things that we do today. The identity of the tools have changed slightly. We're not doing distributed processing in Hadoop. We're doing statistics mostly in Python rather than R. But one of the things that I think is true and stays true is to communicate the results to other members of the organization in a clear and concise fashion. And that is one thing where I think cross-disciplinary academic researchers are forced to do well. So if you're a machine learner trying to work with virologists or with yeast biologists, you will have to learn how to communicate well to somebody who speaks a very different language from you. And that skill, which multidisciplinary researchers in academia foster all the time, turns out to be very useful in industry as well. Okay, so just to put an infographic on it, for those of us who were doing data science a decade ago, you couldn't say the word data science a decade ago without showing this infographic. It was an infographic put together by my friend Drew Conway when he was a graduate student at NYU, trying to summarize conversations happening in New York City around the field data science. And his little Venn diagram here is arguing that data science is the field that you get when you try to apply the craft of machine learning to some other field for which there's already substantive expertise. For example, Haemophilus influenzae, understood or identified in the late 19th century. Suddenly you have an abundance of data about Haemophilus influenzae at the end of the 20th century in the form of its genome. How do you put machine learning tools to work to try to answer questions from people who have been studying Haemophilus influenzae and they already have plenty of substantive expertise? Or for example, a virologist, or as we will see, people in the business of rating books or selling movies or distributing movies or publishing the news. There's a common set of challenges, I would argue, when a field for which there's already substantive expertise suddenly becomes awash in data. By the way, I should point out some things about this diagram. In the upper left-hand side, when he says hacking skills, he doesn't mean breaking into things. He means trying to get a computer to do whatever you want. And in the lower left, or the left side, the danger zone is real. The danger zone is the idea that you really should have some principles, preferably mathematical principles, when you look at data. Otherwise, you will torture the data enough that the data will confess to anything that you want them to say or that your boss wants them to say. So it's useful in approaching large data sets to have some sort of principles. Good. That is really the sort of tagline or the mindset that I've used in trying to help the New York Times build up a data science team. And we focused really on developing and deploying machine learning solution to newsroom and business problems. And I'll try to tease out in our next few minutes together some examples of that. I'm going to draw heavily on techniques that are known well to machine learning researchers from academia and industry, but try to illustrate how a company like the New York Times might reframe those, might take their own questions and reframe them as machine learning tasks. But one natural question to ask is where, even at the New York Times, would you go about putting a data science team? This is a natural question to ask. If when you think about the New York Times, you think about the New York Times as a newspaper, which to be fair, it has been since 1851. It's an old company. And the transition to digital for journalism has made many, many changes. But one of the changes in journalism has been that every interaction with the reader is really a conversation. Whereas if you just publish a newspaper and you print it and distribute it, you don't really get a lot of feedback from readers. And on the other hand, if your product is a digital product, you get abundant conversations with readers all the time. The other transition, I would say, of moving to digital is a real sea change in the way that the business of newspapering is done. So the craft of journalism has been largely harnessed to the business of newspapering. And the business of newspapering, particularly in the United States for the last century or two, has been about advertising. So there's been an incredible sea change with the transition in the way we communicate information as we move from paper to digital. One of the other changes has been the way that advertising is done in the digital realm. And that the craft rather the business of advertisement has been really optimized by a couple of digital companies, including, as you'll see in this graph, Google and Facebook, and less so traditional newspapers, whose advertising revenue has been steadily decreasing for years. In a way, it's been an exciting time in journalism, at least in the States, because every journalism company is now in the search for a scalable and repeatable business model, which is one definition of a startup, search for a scalable and repeatable business model. So it's an exciting time to be in journalism, to think about the changes in the business of newspapering, and in particular, the change away from an advertising-driven dominant model. But the New York Times takes this seriously. You can tell that they take it seriously because they wrote a report on it in 2014, which is usually just called the Innovation Report. And one of the recommendations in the Innovation Report was to rethink the traditional organizational chart of journalism companies. So a metaphor that's a particularly American metaphor, this may not translate well, is the metaphor of church and state, with the idea that you might have a community, or in this case, a company, that has a sharp dividing line between people who have a craft and people who keep things running. The church and the state, in this case, the church is journalism, and the church is represented by the people who possess and defend the craft of journalism, and state is everything else. And it's important for people to be able to trust what they read by journalists, to know that those things are kept separate. So one of the recommendations of the Innovation Report was, given the abundance of data that a transition to digital creates, how might we use data to advance the interests both of church and state? Could we use data not only to create new data products and to improve processes, but also for people on the church side to really enhance news judgment, not to get in the way or to replace news judgment with an algorithm, but to enhance news judgment. And for our readers, with whom we want to transition from an advertising model to a subscription model, to have more of a dialogue with them, because part of the idea of a subscription model is that your interests should be very well aligned with the readers if they are going to be the ones who become the customers, meaning become the paying customers, as opposed to the advertisers being the people who pay you, in which case the readers are, so to speak, the product, which, by the way, is a common phrase in the advertising model since the 1970s, that the readers are the product. Good. So things have gone well at the Times. To be clear, that was a couple of doom and gloom slides. So to be clear, things have been going very well. The transition to subscription is not easy, but we're faring well. And it's been true since really 2011 or so that the dominant revenue source has transitioned from advertising to subscription. And there's a lot to be said about how data can be put to work to do that, which is part of what the data science group at the New York Times works on. Now then, to put that to work, as I said earlier, communicating with other people in a clear and concise fashion is useful. I think that's true for all data scientists in academia and industry. Part of that is to use words that other people can make sense of and integrate into their lives. One of the paradigms I've been trying to advance, at least at the New York Times, is when we're working with people who are not from our team, to try to think about whether or not what they're looking for is a description of some very complicated data set, or are they looking for a model that predicts what's going to happen in the absence of some intervention, or are they looking for a prescriptive model, meaning an example where we have a bunch of data and we try to say not only what is the outcome in the absence of treatment, but what is the treatment that will maximize that outcome. And in fact, those are very different types of modeling, as I'll try to illustrate in the next few minutes, both in terms of the techniques used, but also in terms of the way one designs, for example, an experiment, rather than having no experiment where somebody just hands you a data set, or having a case where the experiment was done already and you don't really get to learn how to intervene. These are normal words that our friends in product and marketing and advertising understand. Within my group, I generally try to say the descriptive models are mostly corresponding to unsupervised machine learning. Predictive models are usually corresponding to supervised learning. And as I'll illustrate, some of the problems that are really in decision support can be reframed as reinforcement learning. So let me use that paradigm to try to organize this list of examples, first with some examples of where you might simply want to describe large data sets in journalism. One example is trying to describe all of our articles as different topics. So an example of where we put that to work was in recommendation. So not now, but then, meaning like 2015 or so, the New York Times' approach to recommendation was to have a little widget on the lower right-hand side of the homepage that simply said sort of a structureless feed of things that are recommended to you. And you'll see that it has a mixture of sports and books and opinion, and then hard news that just happened, investigative. It's pretty much a melange of different topics and reader needs, so to speak. But the way we did that was to build a description of all of our data in terms of topics. The type of modeling in natural language processing is called a topic model. And the idea is to take a corpus of documents and to learn a predictive model that says, for every document, can I say it's a mixture of different topics? For example, an article about, America in Iraq is quite clearly about politics and government, but an article about movie review is quite clearly art, and something that involves a museum in New York City with a contested renovation plan is somewhere between art and government. That is relevant then because you might want to suggest different articles to different people based on what topics they have read in the past. As a graphical model, one of the approaches that we put to work here was one written by my friend and colleague Dave Bly, called a collaborative topic model. If you are coming from a community where you've seen generative models before, you will know what these circles mean. They mean random variables. In this case, the filled-in data the filled-in circles are data, like the words in the article or the response of the reader I to document J. And then everything else is something that you try to infer. For example, for every article, what mixture of topics represents that article? And then for every reader, what mixture of topics is that reader likely to identify with? This is a paradigm also quite widely used in academia. As an example of where I put it to work in working with medical people is a paper on electronic health records where we did something similar. We took electronic health records for patients as along with their labs values and broke it into different topics where the topics could be interpreted as different phenotypes. So that a doctor might look at somebody's patient record, which for somebody who visits the hospital many times is quite long, and simply have it summarized for them as a digital product that shows this person has the following statistically significant phrases occur repeatedly in their health record. At the New York Times, however, the same thing can be done to take the summary of all of the documents, break it into different topics, and then the set of people who read those topics, as well as where they are geographically, and make one very simple description of who reads what where. So we worked that out as a sort of a science project, and then an interesting thing happened, which is we shared it with our friends in the advertising group at the New York Times, and they said, "Great, let's turn that into a product." It was new to me as an academic, so we reframed that model as a product called ReaderScope, because marketers from other companies, so somebody from some major company who might advertise on the New York Times, might be interested in knowing who are the readers of the New York Times and who reads what, or what topics over-index in different locations. So we built that out as a graphical user interface so that people from other companies could learn what topics are being over-indexed in Houston, Texas, or Los Angeles, or where are people reading about wine, or people who are business decision makers, what are they typically reading about? So that was a very it was a novel experience for me as an academic researcher to have somebody build out a machine learning model into a visible product. So that's an example of prediction, but maybe I should say examples of prescription, because many famous problems in machine learning are of the predictive type, where we actually want to predict some outcome in the absence of some sort of intervention. In subscription models, the most common example of these is simply to predict for your new readers, which of them are likely to become subscribers, and for your subscribers, which of them are likely to stop paying for their subscription. So this is a very common type of modeling. I would say it's quantitative marketing 101. And so we did that. So that was one of the first things we worked on, was building something that could not only tell you who are the at-risk readers, but what are the risky behaviors, so to speak. So again, in a public forum, I can't go into much detail about which attributes of reader behavior turn out to be the risky behaviors or the behaviors that engender loyalty. But this turned out to be very useful for helping our friends in product and marketing and business understand what are the general reader behaviors that engender likely to subscribe and subscribers likely to remain. Again, that's an example of a balance between predictive power and interpretability. This was something I had seen many examples of in working with natural scientists and academia. As an example, one of the early works we did almost 20 years ago was to look at microarray data from yeast, which is a model organism. And microarray data were, still are, a technology for allowing you to assess which genes are overexpressed and underexpressed. So early days, we built out predictive models that based on the sequence data in the regulatory region upstream of the genes, and based on the expression data of other genes that are thought to be drivers of expression, we could make predictions for which genes were going up and down. And we rapidly realized that our yeast friends didn't really so much care about our predictive powers. They wanted to know what are the revealed transcription factor binding sites, because it suggests to them what experiments to do in the future. So I would say that's an example of where data science, separate from machine learning, involves this very human craft of trying to reframe problems in a way that's useful to somebody from a complementary domain. They may not be a machine learner, in which case their cheap question is, how predictive model can you build? They might be somebody from a domain where they want some interpretation, something that helps them decide what experiments to do next. Again, I'm not the first person to make this observation. Going back to Leo Breiman's essay, where I advertised Leo Breiman's essay from 20 years ago as being very articulate on this idea that in the real world, people both want predictive power and interpretability. He himself grades his own methods. He was associated with a method called random forest. And as he says in this particular part of the paper, random forests are A+ for predictors, which in the United States is a good grade, but they are F for interpretability, which is a bad grade, fail. So it's been well understood, I think, in applied computational statisticians and machine learners for a while that there is a tension, and then in the real world, people are interested not only in predictive power, but interpretability to somebody from a particular domain. So as I said, an example of a predictive problem at the New York Times might be simply predicting which users are going to become subscribers, which subscribers are going to cancel. But we can really help the community inside the New York Times by building things that are not only predictive, but also interpretable, because these are behaviors that people in marketing or product might be interested in influencing. So in a way, it's building a model not just for showing that you can build a model, but because people want to change the way they want to change their decisions. Good. Where might you have examples of predictive modeling in the newsroom? So one example of a project that we worked on that was an example of computer-assisted reporting was to work with a reporter who had many, many examples of crash fatalities of automobiles, in which she thought that one repeated pattern might be the presence of a particular defective element, namely an airbag used by some major companies, but originally created by a different company called Takata. So we were working with Hiroko Tabuchi. She had this very large database of crash records, and her sense was that some of them were interesting and that she might report out that particular accident, and some of them were less likely to be interested to her. We asked her to label some of these example records as being interesting. We imported this large government-provided XML file, put it into Python, made it rational, and then we wanted her to believe the results of the model. So we needed to make something that was somewhat interpretable to her. So we made a model that could work with word phrases, and we could show her if the phrase "suddenly deployed" is in the record, then you will probably find it interesting, or if there were words like "exploded." But if there were words like "did not deployed" or "deployed but," then you're less likely to be interested. And this is real artificial intelligence, because there's one intelligence we're trying to make artificial, namely this one reporter in her very, very large database of haystacks from which she wanted to find the needle, using the phrase "needle in a haystack." So that turned out very useful for her. She ended up writing a series of articles in the fall of 2014 about this particular case, and it ended up leading to a set of recalls. So this is a Google search term graph, just to show that interest in this topic definitely was spiking in that fall. Another example of putting machine learning to work in the newsroom simply for prediction is in trying to help the photo editors at the New York Times rebalance or retone the actual digital image files so that they are appropriately toned for print. So the New York Times still prints newspapers. And if you take an image as produced by a photojournalist camera, you may find that it's too light or too dark, or somehow doesn't have the right amount of contrast. And then it takes a bunch of laborious pointing and clicking by photo editors in order to get it ready eventually to become ink. So as a form of data exhaust produced by all the editors do this work, we have this amazing before and after training set where we can take as input the original image and then take as output a prediction for what the editors or even what a particular editor would do to that photo to make it ready to become ink. So we were able to, what you're looking at here is actually a test train figure. It's a figure of examples of images as provided by photojournalists as the image file comes out of their camera, a prediction from our model of how we think an editor, a very infinitely patient editor, would retone or rebalance that image, and then an actual example of what an editor actually did when that editor had that image to make it ready to go to print. So then instead of having the laborious long time that it takes to rebalance it, we can give the photo editors a warm start, so to speak. We can give them a good initial guess. These are image data, so it's unclear what features you would use. We use convolutional neural nets and leveraged heavily tools from Google and others for doing deep learning in order to take as input an image and takes as output a new image. A different example of predictive modeling, one for which you simply just want to make a prediction, you don't want to make an intervention, is a form of sentiment analysis on the articles themselves. So we started out with this summer intern project, which was really just a research project to ask, how could we predict if a given article is sort of light and funny in tone or very serious in tone? And we expanded that by asking, could we take an article and just predict what feelings that article will evoke? So this became a summer research project. It was sort of sciencey. And then we happened to mention it to our friends in advertising, and they said, great, let's turn that into a product, which again was news to me, that you can do that. It's not the kind of thing that usually happens to me in academia. And so we turned it into this product. Internally, the project was called Project Feels for, we had a project to see if you could predict what feeling an article would evoke. So how to do that? So we actually did some collection from the internet. So we created a computational framework that would allow us to ask people to look at articles and to say what feelings they felt. This was definitely new to me coming from computational biology, but apparently you can do this. So we did it. And we didn't really know how you should decide what feelings. So we went to some journal article about what feelings exist, and they had a list of 31 feelings. So we started out with that to try it. And once it became a product, however, our friends in advertising realized, advertisers are trying to advertise next to certain types of articles. They're actually very careful about what content their article appears next to. This is, by the way, something that's being debated quite a bit around Twitter. Is advertisers are really careful. They don't want their advertisements next to really off-brand content. So it turned out that this was a good idea to take this algorithm, which could take as input the corpus of an article, take as output a set of feelings that readers might feel. And then an advertiser from a different company could say, I want to have my brand, my advertisement, next to an article that makes people feel happy or of interest or adventurous. And that turned out to be a very successful project. It was successful statistically, but it was also successful in that people actually are paying for it. So in the end, that became a product called prescriptive targeting. We launched it in 2017, and we realized there were only a couple of feelings that advertisers were interested in predicting. So those are the ones which we now predict all the time. And if you'd like to know more, this has been written up in advertising journals. This is a trade publication called Pointer that wrote an article about this new product back in 2019. It was also an opportunity to do a bunch of weird science that I hadn't done before as a computational biologist, like looking at people's responses to different articles and seeing, well, articles that make people feel this emotion also feel this other emotion, which was sort of fun computational social science, which was new for me. Okay, so those are all examples where you simply want to predict an outcome in the absence of treatment. It's not the case that there's some particular treatment that you want to create. However, many problems in the world are ones where you actually don't want to just know what the outcome is in the absence of treatment. You really want to know what treatment you should create. This is true whether you're a doctor or in robotics or business. It's less true in computational biology where you're studying a model organism, but it's a natural paradigm for many things in industry. So I'll give just a few examples briefly. One is from the original innovation report in 2014. If you look at the beginning of the innovation report, it says, we, the New York Times, are not keeping up at the art and science of getting journalism to readers. What that means is After you publish the article in the digital world, you have to decide how to promote that article. And so promoting that article might be via Facebook or Twitter or some sub-channel of Facebook or any number of digital platforms, because ultimately people are not experiencing the New York Times on paper all the time. They might be experiencing it in the palm of their hand and some other third-party application. So we reframed that as a problem in which you could predict engagement with an article as a function not only of the article, but also a function of how it was promoted. So how you promote the article is like an action, it's not an attribute of the article itself. So we did the work, we built the machine learning, ran it all in Python, and then we realized, how are we going to get editors, the real human beings, to use this? Because we cannot get editors to run Python. We cannot get editors to stop what they're doing and open up a new web application. Fortunately for us, the editors at the time were really falling in love with Slack. So Slack is basically a chat program, but it's extremely programmable. So you can write apps that are part of the Slack environment. So editors are spending their day in Slack, and they can simply interact with a different account, which in this case happens to be a bot. So many of our editor-facing machine learning projects right now are actually instantiated in the form of a Slack bot. The oldest is this bot called Blossom. Blossom because when you have a flower that's growing, you pour water on it, it blossoms. And Blossom can suggest to an editor places where you might promote an article. You might want to promote this article on a particular sub-account of Facebook, for example. To be clear, though, the editors sometimes can set it to interrupt them and alert them, or the editors can ignore it entirely. It's an example that draws heavily on academic literature. So, for example, John Kleinberg of Cornell, Lars Backstrom, who was at Cornell at the time, had written this great paper with somebody at Yahoo about trying to figure out when should you publish stories. And Lada Adamek, who by that time had already left Michigan for Facebook, had published another story on just trying to see if you can predict which posts will go viral. These are all examples of academic literature that we were able to draw on. I mean, I say academic literature, but they were clearly at the intersection between academics and industrial researchers. The other thing I should say is it's an example where we have a prediction problem, but really it's in the context of a question, like what should I be doing as an editor? I should also emphasize that this is not an example of humans out of the loop. This is very much human in the loop, because editors, inquire, but they absolutely don't always take the advice of Blossom. Sometimes they ignore it entirely. That's an example where the goal is to actually derive a decision rather than to make a prediction alone. Other examples. Another example in which there is not a human in the loop, but it's totally automated, is the question about when to ask somebody to become a subscriber. So the way this is delivered at the New York Times, and has been since 2011, is with a digital paywall. So somebody's reading an article and then suddenly they have to stop and the paywall says, now is the time when you should become a subscriber. We actually do this using machine learning. So we do this by deciding for different people, what is the number of free articles they should get. Learning this involves thinking clearly about what is it that you want. Do you want people to become subscribers? Do you want people to engage? Or do you want some sort of Pareto optimization between the two? Because you're actually doing an intervention, it's not statistically meaningful to make a predictive model based on observational data. In this case, you actually have to have interventional data where you have attempted the action and then you've learned the causal effect of the action. Here the action is, how many articles should a person read before we ask them to become a subscriber? So the only way to do that, or the best way to do that, I will say, is actually to do an experiment. In this case, we did randomized controlled trials. An idea from statistics that's 100 years old, but is less used in, say, computational biology, in which we actually randomly showed a small set of people different numbers of articles before we asked them to become a subscriber, and then we could learn the causal impact of that choice. Tuning between two different things is an idea that's known well in constrained optimization. If you've ever used a Lagrange multiplier to say, I want to optimize this, but a fixed value of that, we basically do the exact same. But for our friends in business, that means that they have a knob that they can turn between how important it is to have subscribers now, versus how important it is to have many engaged readers now, under the hopes that those people will eventually become paying subscribers. So we can deliver different amount of friction or different openness of paywalls to different readers. We can estimate from previous data how well a new policy will perform. You could do that again because you have randomized controlled trial data. Is particularly useful to form these estimates. These estimates turn out to work pretty well when we actually deploy. And as I said, we can derive this sort of Pareto front so that our friends in business can tune a knob between how much they want a short-term return and how much they want a long-term return. The ultimate, though, in taking humans out of the loop is recommendation engines, in part because we're in the news business and news changes very quickly. And so we don't ask editors to decide minute by minute for all of the 600 stories that are put out every 2 days, which story should be sent to which person. So this is a good example where we're actually going to use reinforcement learning. So if you don't know reinforcement learning, it's a type of machine learning that's been getting a lot of attention in the last decade, particularly in the context of playing games. Games are cases where you have as much data as you want. And it's part of the marketing of many companies that they'll have deep Q networks, for example, as a type of reinforcement learning. Or you can, there's some high visibility papers where you can show that reinforcement learning can help you learn how to play computer games. The real world, however, is not a game. We have a finite amount of data. And so we end up leveraging heavily a technique, which is called the multi-arm bandit approach. So if you haven't heard this term, it's a term that actually has an old history in statistics. It was first used in this paper in 1955, where somebody made a physical device where you choose somebody to choose outcome on the right or outcome on the left. And there's a tantalizing footnote in this paper saying the optimum decision rule seems not to be known. And the truth is that was the start of a really interesting statistical literature on trying to figure out when you interact with the world, how do you figure out what is the best thing to do? So this is now common in many companies that it's a personalization approach. If you show different outcomes to different people, that's the same as saying that the best thing to do is different in different contexts. And so the technique is called not just bandit, which in the United States, bandit is a metaphor for a one-arm bandit, or a slot machine is sometimes called a slot machine is called a one-arm bandit. Contextual bandits is the idea that you learn a model which does the best thing for the right person. And there's a natural context for personalization. So we've been doing that at the Times. It's been a big upgrade to what was originally a very simple recommendation approach from 2011. To be clear, personalization is not new at the New York Times, but doing it this way is. So that when it was first served as a sort of structureless web page for each person, or in the lower right-hand side as a structureless feed of articles. I've told you a little bit about how you might do this as a descriptive approach, but to be clear, what we're doing now is trying to do this using stochastic optimization directly. So if you'd like to read more about this, there's a nice article about this by Dr. Anna Konen, who now leads the algorithmic recommendation team. Her background was in cognitive science, but she's rolled up her sleeves and become a software engineer as well. Partly what we've learned about this is if you want to optimize, it behooves you to use techniques that are directly prescriptive rather than descriptive. It allows you some flexibility to be really complicated and use deep learning, or to use very, very simple linear models if you want something that's more interpretable, which can be useful for us who are developing the algorithms, but also our friends in the newsroom. And so now we deliver this on actually multiple surfaces. It's not just one structureless feed of everything that's popular. It's also things that are in specific sections. So at the end of a story, you might find that stories that are recommended to you are particular to that section, or it might be editorially important stories that the editors pick every day, a list of stories that they think are really newsworthy. Or it might be lifestyle journalism, which at times is sometimes called smarter living. Or you might find it in the mobile app under a section called For You, or in a personalized newsletter called For You. This is an image from the app. And also there's the cooking content. So one fun machine learning problem has been to realize how different is recommending news from recommending recipes. So we have a cooking app, it's a huge corpus of recipes. Those recipes are not news, so it's not like they are interesting only for half an hour. They might be interesting forever, or they might be interesting once per season, like Thanksgiving or Christmas relevant recipes. So that's been a fun machine learning problem. Okay, if you'd like to know more, Dr. Cronin has a great blog post about it. Key ideas to keep in mind here are the important role of experimentation, how much more you can do with machine learning if you actually get to interact with the world and learn by intervening. And that the particular approach we've been leveraging is this one called contextual bandits or contextual multi-arm bandits. Just for those of you who might be somewhat curious about what's going on here, the idea is to take a randomized control trial and gradually upweight the probability that you show people the variant that seems to be the best. So it builds on a long-standing statistical tradition from Fisher of the randomized control trial. but it obviates problems of p-valueology. You don't need to run a randomized control trial and then think really hard about the p-value. You don't need to have a meeting and say which variant got the best p-value. You just let the algorithm go. In the interest of time, I don't think I should go into mathematical details. So I'm happy to talk later about how you might do this. There's some very simple approaches. My favorite thing is that the most favored approach is actually really old. It's from 1933. It was completely ignored by everyone for 85 years. And then suddenly people realized that it was actually optimal in multiple senses of the word, including like provably optimal. And so suddenly this technique became the bee's knees in machine learning, which is very reassuring. If you have a paper that you think is great, but nobody's citing it, maybe it's just that you're 85 years ahead of your time. Also, in the interest of time, I don't know that I want to spend a lot of time on the way that this has impacted my research wearing my academic hat, but to say briefly, these challenges of building interpretable and performant bandits for news has motivated a number of papers that I've been working on in my Columbia hat. How can we use variational methods from statistical physics? How can we use Monte Carlo methods to deal with problems that the world changes in time? How can you use techniques from sequential importance sampling? We haven't put these to work at the New York Times, to be clear, but it's motivated a lot of the work that I've done at Columbia, trying to understand bandits better, or even to understand them in the language of dynamical systems. So one project, which is I'm still writing up right now, is how to take this problem of trying, it's been proposed since 1955, of how do people figure out which is the better button to click, but repose it in the language of dynamical systems. Again, in the interest of time, I don't want to go too much into using variational methods. It leverages similar techniques to something I've already mentioned. If you've ever encountered non-parametric methods, you will recognize some of the algebraic form here, that it's a technique which allows you to build models that get more complex as the world reveals to you that the world is complex. And if you look at this literature, it's a literature in which the smallest regret is the best method. So in papers like this, a typical curve is how many mistakes did you make as a function of time? And a good method is one that in the long time makes the fewest mistakes. Again, I don't want to go too much in the mathematical methods in the interest of time, because I want to leave some time for questions, except to show that these methods work, including methods that leverage the language of dynamical systems for a problem that I would say for the last 75 years has been more attacked by machine learning people rather than dynamical systems people. Instead, I want to close with some lessons learned, and if people in Q&A want to hear more math, I can talk about math. But the lessons learned are, because data science is often about working with people who are complementary to you, often the success of a project, or in our case, a data product, is much more a function of getting the right people on board and then understanding what other people find interesting. For example, you might have a science project that you think is fun science, and then you talk to somebody in a different organization, you realize that that project is actually very useful to them. The other thing that is different from academia and industry is the role of infrastructure. So often in academia, the data set we're looking at is a CSV file or something very simple that somebody hands to us. But in many problems in industry, you're dealing with streams of data that are produced by engineering systems whose distribution is changing in time. And there's a lot of work to be done to make sure that the data pipelines are correct. There's a lot of work with data analysts to sort of reveal gaps between how you think the data were created and how the data really were created. And having all of those things in place is requisite before you start building machine learning methods if you actually want to impact somebody else's process. Again, this is not an idea new to me. It was well articulated by Monica Rigatti in a blog post in 2017. The other idea I would say is how useful it is to think differently about description, prediction, and prescription as a data table. One way to think about this is in descriptive problems, somebody hands me a big table of data. In prediction problems, somebody hands me a table with one magic column, and I want to predict that column from every other column. That's the usual context for many machine learning problems. However, if you're in robotics or healthcare or industry, often it's about making the right decision. So those are contexts in which the data table somebody hands you is one with two important columns. One is the outcome, and the second is the treatment that was given that should be driving that outcome. And those problems really have a special and very valuable character. The other thing I'll say is that building up this team is certainly not something I've done on my own. It's been a joy over the last 9 years to build out a team of people coming from a variety of backgrounds. Just mentally. For me, looking at these people, I know that they're coming from electrical engineering, physics, cognitive neuroscience, geophysics, biophysics, computer science, biology, politics, theoretical chemistry, mechanical engineering, and statistics, a wide variety of fields, which I think has been very useful for all of us, bringing fresh perspectives to these very, very interdisciplinary problems that we face in industry. And as I said, if you'd like to know more, please do feel free to email me wearing either of those two hats. And if you'd like to know more, there are two books you might consider. The book on the left is really for practitioners. It came out in October. And the book on the right is really for everybody. And that will be out in March. And with that, I think we have a bit of time for questions. Thank you very much.
Thank you very much. Are there any questions in the audience? Just raise your hand and we'll try to unmute you. Maybe I do one for warming up.
Thank you.
How do you motivate people to actually click on these surveys after the articles? Like to say what mood they are. They get like anything in return? Or was it like they were just motivated to help the New York Times?
Absolutely. That's an excellent question. So that's done on an entirely separate crowdsourcing platform. And so people are actually paid, they're actually paid by the task. So it's a survey tool, it's a computational survey tool with a separate closed world environment. So it's separate from the New York Times itself. It is not the case that we take readers and ask them in the course of their reading. It's a separate computational platform in which people are paid by the task, which was one of the things that, so when somebody said to me at the New York Times, wouldn't it be great if we knew what was hard news and what was a lighthearted tune? I said, well, that would be great, but I don't have any data like that unless you're willing to pay for me to pay other people to read the things and comment on it. And to my surprise, people were willing to pay for that. So yes, it's been a very profitable data set.
Super interesting, thank you. Maybe a follow-up question. What do I know about myself if I get like only very small snippets of an article shown before I have to pay? Only one or two?
Oh, you mean if somebody's
there's an algorithm who decides to show me more or less free articles. What does it tell me about my
you mean
my online profile somewhere? Yeah. I always feel like I can read only like a very small paragraph before I get asked to pay.
So generally on the so those paywall rules, I should say, also change regularly in time. So by the time that anybody watches this video, the paywall rules might have changed entirely. But generally, when somebody shows up, they get, I believe, either two or I think it's two free articles before they're ever asked to pay. So everybody has some content that they interact with. To possibly our surprise, there actually is signal there in the way that people interact with different content, even people who are not yet subscribers, which content they interact with, how regularly they show up, actually does reveal signal about which people should have access to more articles if we want to optimize for long-term engagement, or should be asked to pay right now if we think that this person would be willing to pay. And when I say we think, I mean a prescriptive algorithm.
Thank you. Is this like done by some cookie technology? How does this work? Is it IP based? I mean, I don't want to ask too far, but
there's not that much that you can learn from people by cookies, and also we try to avoid using any third-party tracking cookies. So for several years now, the New York Times has removed tracking pixels from article pages because we don't want to be sharing with some third party the reading history of somebody. Instead, it's done by people registering. So one policy change by the New York Times several years ago is you can read more articles if you sign in for a free but registered account. And at that point, we have much more of a sense because we can track using our own data. Is this person associated with a particular email address? So rather than using some third-party tracking pixel, which has been a very dominant form of advertising, digital advertising for the last 20 years, we didn't want to have, Facebook or some other third-party data company having access to a reader history. So the way it's done is much more simply, which is simply to say, like, you will read more articles once you become a registered but free reader.
Thank you very much. Are there maybe any other questions in the audience? Just raise your hand, please. We have one. Nicola, would you like to unmute?
Yeah, thank you. Can you hear me?
Mm.
Great. Thank you, Professor Wiggins, for your talk. I have a question on at the beginning of your career. You mentioned that you built the data science teams. What were the first challenges you faced while building the data science teams at the beginning, because it was quite new at that time, I imagine?
There's several challenges. One is the New York Times data infrastructure was, I would say, not as performant and reliable as it is now. And it was also fragmented. So the New York Times, when I showed up in 2013, had only recently created one unified business intelligence team where many different databases were organized with a set of people who sat together and who, because they were in the same place in the organizational chart, were motivated to talk to each other and share information. So you need a lot of data to be available and easy to relate to each other. For example, if you want to relate somebody's reading behavior to their likelihood to be subscribed, you need abundant history of reading behavior, and you need abundant history of who has become a subscriber or who has canceled their subscription. That may seem trivial, but before long ago, this was controlled by one group, one place in the org chart. This was controlled by a different group with a totally different data schema in a different part of the org chart. So that's a challenge. That's just an organizational challenge. I mean, it's a data infrastructure challenge. So that challenge needed to be met. The second challenge was simply for me to understand, well, what are people's problems? Because, if you show up to a company or to a community and you say, oh, well, biologists, what you really should want is something that tells you the distribution from which data are drawn or something like that. And maybe the biologists don't really care about that at all. So there's a collaboration challenge, which is to meet somebody from a different domain and make sure that you're building something people want, or that you're solving a problem that people actually have. I think that's true in cross-disciplinary science as well as in industry. I would say a third challenge is just making sure that people understand what data science can and ultimately can't do. So as a data science team, if you're a new capability in some community, in general, people won't know about you or have an understanding of, an imagination for what that new capability can bring. So it took a while to try to explain to people, here's what the promise is of data science. I hope that answers the question.
Thank you.
Thank you very much. Maybe we ask a last time if there's another question. Don't be shy. Doesn't seem to be the case. So then maybe let me say some words of closing for the seminar.
Please.
Thank you so much, Professor Wiggins, for your presentation today. Thanks to all of you for attending and the discussion. Let me just briefly remind you that we have the EPFL CIS NeurIPS 2022 regional post-event coming up this Wednesday at Lausanne campus in Switzerland of EPFL. If you're in Europe or Switzerland, feel free to pop by. We still have a couple of seats free. It's going to start in the afternoon. More information on our website. And then in January, we take up again our Colloquium series with the talk of Professor Zaha Teichmann. She's going to join us on January 9th for her talk. I wish you all a great day and I hope to see you soon. Goodbye.